So this is kind of a basic approach, illustrating a sort of general class of techniques for, or let's say one general class of techniques that are movement-based for identifying objects or events of interest from a video stream.
Exactly.
So, typically I would expect that people developing these kinds of algorithms would be doing it on a PC. But then if it's going to be deployed, like imagine this kind of security application that you were talking about on a light pole in a parking lot, that's probably not going to be a PC. It's probably going to be some sort of embedded processor.
Correct. So really, PCs are more or less the prototyping, the R&D environment for computer vision. This is where an algorithm engineer is probably most productive, trying out new ideas, trying out different models that we talked about, and getting the parameters right and tweaking the solution itself. And then what needs to happen after that is that transition from PC-based solution to an embedded based solution. And
so in this case, you've got an embedded implementation of this algorithm running on a TI DSP?
That's correct. What we have here is the DaVinci DM6437 evaluation board, which features the exact chip and has some input ports, output ports, so that we can start playing with cameras and demonstrate capabilities such as this one.
Great. And maybe you could talk a little bit about how one would get from a PC prototype into an efficient implementation running on an embedded DSP like this.
That's a good question. So typically, a couple of things needs to happen for an algorithm to really map effectively and successfully onto an embedded platform. I will say the first one is a careful consideration of the algorithm itself, so that the complexity is actually amenable to an embedded implementation. Secondly, in the big scheme of things, the representation of the information, of the pixel values of the model, needs to be mapped well to the capabilities of the hardware, and as well as to the requirements of the application. If we are in quick and dirty prototyping mode on the PC, let's say we are using OpenCV, MATLAB, Python, our favorite tools, it's probably not very important to worry about things like fixed point. We can just go ahead and implement things in double precision floating point, and when we are first coming up with the solution. But when you want to go to the next step, you want to sort of start making those design choices more carefully, and really vet your algorithms with respect to most effective representations that you'll have on the chip. So part of that is really looking at your variables. Are they in the right type? Fixed point, floating point. And after that, taking a careful look at the flow of your algorithm, of your solution. You don't want to be pushing in and out of the memory entire images, entire frames. That's something people are learning with some pain, actually, when they try to go from OpenCV to embedded. So it's really important to be fully aware of the big picture before you step in and declaring, this is the code I want to really run on my product.
So hopefully from the outset, as you're devising the algorithm, you have the kind of idea in mind of what sort of resources, data types, memory footprint, memory bandwidth, processor power is available to you, so that you're not designing an algorithm that's not going to fit in the target the target processor. And I assume then, or maybe you start without any constraint, but then once you have an approach that seems to work, maybe you look at, well, how can I simplify, still on the PC, but simplify the algorithm so it's more likely to fit in the resource envelope of the embedded processor.
Correct. And it goes both ways. Sometimes the solution could be actually too simple and too lightweight for the hardware choices you made. So it's really you need to find the right engineering solution. So it's not always the story of, I had to dumb down my algorithm to make it fit. It can also be the other way. For an effective, cost-effective product, this is the right chip. This is the right complexity and we don't need 10 times more power consumption and price tag really for a solution. So it's really you want to get that in the ballpark right.
So at some point, I assume you've got some C code, for example, on the PC, and you're going to recompile that for your embedded processor.
Exactly. So in this particular case, this particular device has a C programmable DSP. This is actually a generic. You can run arbitrary C code on it, compile for it, and run it, and it will work just fine. And so, which means from the very beginning, as long as your solution is in C format, you are more or less good to go. It will run. It's not probably going to be in the most effective way, but it will be functional. So the frame rates, the resolutions you can handle, will probably need some more work. And we actually have come up with a collection of libraries to help our customers in this process. Early on, even when they're on the PC, they can start looking at our APIs, looking at our different vision imaging libraries, and get an understanding of what is already optimized, what is already available on these embedded processors. And we even went to the extent of creating PC versions of these libraries. So you can actually, in the middle of your PC development environment, you can actually pick and choose and drop in, let's say, a vision library kernel that will behave exactly the same way on the PC as it does on the embedded platform. So that as algorithm owner, you don't have to worry about divergent results, different behaviors, functional behaviors from one platform to the other one.
So this is a library of vision functions that TI has optimized for the DSP.
Correct.
But also provides non-optimized PC versions for prototyping purposes.
Exactly.
I guess the advantage of using that library versus something like OpenCV would be that in the OpenCV case, the optimized implementation doesn't exist for the DSP, so I'd have to do that myself.
That could be one of the reasons. It's actually a multifaceted problem. It can be an API mismatch, the way you will do things in an embedded friendly fashion versus the way you will just do it without thinking too much on a PC. So it's important to acknowledge that sometimes at the API level there are differences. So once you go embedded, really, for a cost-effective product, again, that's being our golden goal, a lot of times what you end up doing is you do some processing on your data, let's say your incoming image, and then while you have the data and the intermediate results in your fast memory, on-chip memory, let's say L1, L2, you want to do as much processing on that data as possible right there. You don't want to wait until that model update wraps up for the entire frame. No, you want to work on typically chunks of image, all kinds of processing done on the same chunk before you declare you are done with that piece of image. And interestingly, this has API implications that are not always acknowledged, but little by little we hear our customers mention it. Everybody's getting educated, over time. And I'd like to show one example here on this slide, where here's a IAR filter example, where we are showing basically the function and the parameters it takes. And as usual, here's your pointer for the input image, here's your pointer for the output image, here are the pointers for the parameters, and we see this extra stuff that we call scratch buffer, maybe multiple scratch buffers. What these are doing is they are giving you a chance to reuse some data you might have already on your memory buffer. You don't have to use them. If they can still be in DDR in external memory, and you can still rely on cache to bring those in. It will still work. But if you are going to be pushing the limits of optimization and really caring about the last few cycles, you will want access to those scratch buffers, and you will want to enable your algorithm to really fit into this flow, where kernels are followed by each other and they are all working on the same image portion or intermediate results of those images.
That makes sense. So I think you have some performance data here that where you can show the sort of vanilla C code version of the
Sure.
algorithm running on the embedded DSP, and then another version using the optimized
Exactly.
Functions, and I guess also an optimized flow of data through memory
Exactly.
as well.
Exactly the point. Yeah. So let's pull up the list of functions that enable this application which we talked about. So if I turn on this switch, basically, what we're going to start seeing on the screen is kernels, functions that were used to put this together. We already talked about this, just to refresh your memory. Here's your update exponentially weighted running mean and variance kernels.
Mm-hmm.
To fill you in about the full frame here, in this column we are showing how many cycles per pixel these two functions are taking on the architecture. 17 cycles, 23 cycles. And if you roll them up to match the use case here, which is QVGA 10 frames per second, this adds up to 13 megahertz or megacycles or 17 megacycles on this architecture. What we are showing here is just pure C code compiled for the C6000 DSP target and running actually on the target right now.
Okay. So sort of bottom line here is these functions add up to about 86 megahertz in this unoptimized implementation on the embedded DSP, and it looks like that's about 15% of the
Let's say so,
capacity of this DSP.
Exactly.
Okay.
Yeah. So what we are going to do next is we are going to switch to a DSP optimized code. In this case, these individual functions that you see all happen to be in the vision library, VLIB, that TI has made available to developers. And what we are going to see next is when we turn on to the sped up versions of this exact same code, the usage on the DSP is going to go to much lower levels.
Okay.
So let me turn that on. And this nice graphical user interface, the nice graphics are due to Darnell J, who did an excellent job in putting together this demo. And there's actually some very simple temporal filtering going on to get the numbers a little sort of better behaving. So you remember the 15% loading?
Right.
It is now down to 1.5%. So more specifically, from 86 megahertz, we went down to about 9 megahertz. Because we are now using a DSP optimized code.
Which includes using the DSP optimized versions of the TI library functions.
Exactly.
And optimizing the flow of the data through memory, so we're minimizing the shuttling back and forth, kind of doing everything we can on a chunk of data while it's in level 1
Exactly.
memory, and minimizing the amount of shuttling back and forth of data.
Exactly. So there are two sort of aspects of this sort of full application flow story. There is the compute part, which is relatively easy to quantify. How long did it take for these pixels to be produced? And there's also the I/O, input/output. How much time did I spend bringing data onto my memory?
Mm-hmm.
How slow was the cache? What was the cache behavior if you use cache? So in this particular case, yes, we have the fully optimized implementation that is leveraging the best that the platform has to offer. So when we have a nicely optimized kernel, we get to observe the benefit of using that kernel 100%,
Mm-hmm.
because we have also taken care of the memory flow.
Okay. Now, this is using TI off-the-shelf library functions. What if I have my own function that isn't in the TI library?
Exactly, then you just bring them in. Just like we have compiled the C code here, you will do exactly the same thing. You will be adding your code, your pieces, or your entire application, blend it as you find appropriate with TI libraries or otherwise, and then you'll be compiling for the target and running them on the actual.
What about the
processor.
optimization though? You went, some of these functions went from 15 cycles per pixel to 1 cycle per pixel through some thoughtful optimization of the code by somebody who understands the target architecture.
Exactly.
Presumably I need to do that as well on my functions if I want to get that kind of performance.
Well, yes. So there's a lot of helpers here. So the software toolset that TI has come up with is really meant to make that process as easy as possible. So we have compiler tools that can understand a lot about your flow already. Here, typically in computer vision, the most demanding parts are written in some for loops deep down in your code that are going through, crunching through every single pixel. So the main task of the compiler, optimizing compiler here, is to really pay attention, lots of attention to those for loops, and to come up with really parallelized version of the code.
Okay.
There are different levels of doing this, where you can start by, you can just be sort of a, you can take the minimalist approach and just say, I'm just going to compile my C code and see the performance. And as next step, you can start giving hints to the compiler. Oh, this for loop runs at least 16 times, for instance. Or it runs a multiple of maybe 4 times. Those will be hints the compiler can use to do things like unrolling the loop, analyzing what kind of massaging it can be done on that code. And here I'd like to put in a slide actually to show what kind of optimization progress one can expect. And the 2 functions I'm showing here happen to come from this exact application, the running mean and variance. And in these different columns, what we are showing is the progression, the optimization level. We went as we went from just C code to optimized C code, optimized with intrinsics, where the programmer gets to indicate which exact instruction needs to be used, and then as final step some fine-tuning, again always using the compiler tool feedback. And what we see in these examples are really in front of us examples of 15x speedups that are very feasible when you go from naive C code to a little optimized code. And as you can see, this is always a curve, and there's going to be a point where the returns are not going to justify the investment. So you will be stopping sort of your optimization effort at some point. But it's really important to observe that early on you get a huge boost in performance just by understanding the compiler, the architecture a little bit, and putting in the right hints. And what's our last point here? It is the intrinsics, really. Intrinsics, so you are still writing C code, so there's no assembly going on here. And the compiler did all the register allocation for you. The compiler did the scheduling for you. So the tools have really come a long way.
So the intrinsics give you the ability to tell the compiler, hey, use this particular instruction that I know the processor has. It allows me to do 4 additions in parallel.
That's a good
or something
example.
like that. But I don't have to get involved in writing the assembly code. I just basically tell the compiler, use this instruction.
Exactly. So this data type, it looks like a 32-bit integer, but I know that internally I have 4 8-bit pixels packed in there. So I might want to do like an MPY4, for example, which does 4 parallel multiplication operations on those 8-bit packs separately.
Got it.
So just another quick take-home message that these optimizations are not. This is not rocket science. As much as I would like to sort of claim I might be a rocket scientist, no, it's not really the level of sophistication we are talking about here. Basic understanding of the architecture and leveraging as much as you can, and you'll want to existing libraries.
That makes sense. Well, this has been a really interesting conversation, Goksel. I think you have a few resources that we can point people to if they want to know more about this particular demo or about the TI VLIB Optimized Vision Library.
Definitely. So I'll be happy to. So we did actually publish a paper on this at the Embedded Computer Vision Workshop in 2011. And so here's the paper. And basically the authors you see here are the very ones who have contributed kernels to the Vision library. So it's a good way of acknowledging their contributions here as well as underlining Darnell J's role in coming up with this beautiful demo on the DaVinci platform. And for more information, please please follow these links.
Great. Well, thank you very much, Goksel. Really interesting demo, really interesting discussion, ranging from application and algorithm down to optimized implementation. Thanks a lot.
Thank you, Jeff. Thanks for having me over again. Bye-bye.